Welcome to the new era of video creation with Biozi8. Today, we will discuss optimizing a large-scale deep learning model for deployment on distributed systems. How would you approach optimizing a large-scale deep learning model for deployment on distributed systems, considering both training and inference stages? What challenges might you face, and how would you address them? Large-scale deep learning models typically require distributed systems to handle massive datasets and complex computations. In the context of training and inference, the requirements vary. Training requires the simultaneous processing of vast amounts of data, while inference focuses on low-latency predictions. In distributed deep learning, multiple nodes, servers, and GPUs are used to accelerate model training. The challenges of such systems include managing network communication, ensuring efficient synchronization of models across nodes, and the distribution of data in a way that reduces bottlenecks. This approach helps handle large datasets and reduces training time. There are two primary strategies for distributed training. Data parallelism. This method splits the dataset into smaller batches, each of which is processed on a different device. Each device computes the gradient for its portion of the data, and then the gradients are averaged and applied to the model. Model parallelism. In this method, the model itself is divided into smaller parts, with each part residing on a different device. This is particularly useful when the model is too large to fit into the memory of a single GPU. A hybrid approach combines both strategies, allowing the system to handle both data distribution and model distribution simultaneously. Frameworks like TensorFlow, PyTorch, and Horovod provide tools to implement these strategies. Distributed deep learning faces several challenges related to efficiency and scalability. One major issue is communication overhead. When using multiple nodes and GPUs, data needs to be shared between them, leading to time spent on data transfer, which can reduce overall performance. Synchronization is another challenge, as all nodes must be synchronized in terms of model parameters. If nodes fall out of sync, the training process becomes inefficient or inaccurate. This is particularly important when using asynchronous updates, where the gradient updates might not be in sync across all devices. Scalability is a key concern, as adding more nodes doesn't always result in linear improvements in training speed. Finally, fault tolerance is critical. Node failures are inevitable, and the system must be designed to recover gracefully from failures without losing significant progress. To optimize distributed training, several strategies can be applied. Gradient accumulation helps to reduce communication overhead by accumulating gradients over several mini-batches before sharing them with other nodes. This reduces the frequency of communication, improving overall speed. Asynchronous versus synchronous updates. In synchronous updates, all devices wait for each other to finish their computations before updating the model parameters, which can lead to delays. In asynchronous updates, devices update parameters independently, but this can lead to issues with model consistency. The parameter server approach centralizes the management of model parameters. It acts as a hub where all nodes push their updates and pull the latest model parameters. All reduce algorithms efficiently average gradients across nodes, ensuring consistent model updates without the need for a central parameter server. For real-time inference, models must be optimized for low latency predictions while ensuring scalability. One approach is batching requests, where multiple inference requests are processed in a single batch, which helps reduce per-request processing time. Model distillation is another technique for optimizing inference. It involves training a smaller model, a student model, to approximate the predictions of a larger, more complex model, a teacher model. The student model is more efficient and can be deployed in environments with limited computational resources. For deployment on edge devices, it is common to offload inference tasks to local edge devices to reduce latency and improve response time. Tools like TensorFlow Serving and Triton provide optimized solutions for serving models in production. Scalability is critical in large-scale distributed systems, both for training and inference. Elastic scaling allows the system to dynamically adjust its resources based on the current workload. For example, when training, more GPU nodes can be added during peak times and removed when the demand decreases. Sharding data helps distribute the data across multiple nodes, improving parallelism and reducing bottlenecks. For inference, load balancing ensures that inference requests are evenly distributed across available resources, preventing any single node from being overwhelmed. Finally, auto-scaling ensures that resources are automatically scaled up or down based on demand, helping to maintain system performance during periods of high or low activity. Combining data parallelism and model parallelism is a powerful way to optimize both the computation and storage requirements. With data parallelism, each node processes a portion of the data, while model parallelism involves splitting the model itself into smaller parts. A hybrid approach can be employed to combine the benefits of both strategies. This approach allows for parallel processing of large data sets, while also distributing the model to avoid memory bottlenecks. The main challenge in using both techniques simultaneously is ensuring consistent synchronization of the model parameters and gradients across all nodes, which can be complex to manage and can reduce overall efficiency if not handled correctly. In large-scale distributed systems, fault tolerance is crucial to ensure continuous operation in the event of hardware or software failures. Checkpointing is a technique where the system periodically saves the current model state, so if a failure occurs, the training can resume from the last saved state rather than starting from scratch. Having backup nodes ensures that if a node fails, there are replicas available to take over the load. Replica synchronization ensures that all copies of the model across different nodes are kept in sync. If a failure occurs, the system can quickly recover by switching to a backup node and resuming from the last checkpoint. Model optimization is essential to ensure fast and efficient inference, especially on distributed systems. Quantization reduces the precision of model weights from 32-bit floating point to lower precision formats, e.g. 16-bit or 8-bit, reducing memory usage and speeding up computation without significant loss of accuracy. Pruning involves removing unnecessary weights from the model, which reduces its size and speeds up inference. Knowledge distillation is a technique where a smaller model, the student, learns to mimic the behavior of a larger model, the teacher, making it more efficient while preserving accuracy. For edge computing, deploying the model on local devices reduces the latency by eliminating the need to communicate with a central server for every inference request. In conclusion, optimizing large-scale deep learning models for distributed systems involves a combination of several techniques to ensure both speed and accuracy. During training, using data parallelism, model parallelism, and frameworks like Horovod can help handle large datasets and improve performance. For inference, optimization techniques such as quantization, pruning, and knowledge distillation help reduce latency and resource usage, making models more efficient for deployment. Ensuring scalability through elastic scaling and load balancing is crucial to maintaining high performance across systems. Finally, implementing fault-tolerant strategies, such as checkpointing and backup nodes, ensures that training and inference can continue smoothly even in the event of failures. These approaches allow for seamless operation in production systems, ensuring the reliability and robustness of deep learning applications at scale.